Hi friends, welcome you all. Today we try to understand what are semiconductors and what are its types. Before we start what is semiconductor, we try to understand what is material conductivity concept. And then we will move to how to construct the semiconductors and then what are the semiconductor materials. Afterwards, what are the types of semiconductors, how to construct N-type and P-type of the semiconductors. Later on, we will find what are the major comparison between P-type and N-type of material. Now we start with what is material conductivity. Okay, as a part of which, how many different types of materials are there? With respect to conductivity, we find three different types of materials. One is conductor, next semiconductor and insulator. Conductors are the materials who are having very high conductivity, electric conductivity. Semiconductors are the materials whose conductivity lies between conductor and insulator, and the insulator conductivity is very less. Now we will find what are the major reason for this distribution in the conductivity. Okay, why the conductors are having very high conductivity, semiconductors are having medium conductivity and insulators are having less conductivity. To understand that, we should know what is valence and conduction band and what is energy band gap between valence and conduction band. So we will try to find what are the major reason for the same. You can observe this diagram. So in this diagram, it is clear that for the conductors, the valence band and the conduction band both are merged, as a part of which the electrons present in the valence band are freely available in the conduction band and they will take part in the electric conductivity. Coming to semiconductors, the valence band and the conduction band are having a energy band gap. Okay, if the materials having energy band gap between 1 and 3 electron volt, such materials come under semiconductors. Okay, and coming to the insulators, the energy band gap between valence band and conduction band is 5 electron volt and more than 5 electron volt. Now coming to semiconductor, how can we bring the valence electrons present in the valence band to be available in the conduction band? There are four different ways how can we make the valence electrons present in the valence band to be available in the conduction band for the electric conductivity to happen. So first thing is on introducing or on exciting our material with temperature. If we increase the temperature of a material, then the energy of that temperature will be accepted by the electrons present in the valence band and they will shift to the conduction band. Once they shift to the conduction band, they will take part in the electric conductivity. Here, on increasing temperature, it is not only the one example so that I can make the valence electrons to move from valence band to conduction band. Other than that, photon of energy, if we make fall over the semiconductor, then also the valence electrons will move from valence band to conduction band. Other than that, by using a magnetic action also we can do this process, but usually in case of semiconductors we prefer to go for doping process. Okay, doping is a process wherein an impurity is added to the pure semiconductor to make the valence electrons present in the valence band to be available in the conduction band. Okay, usually we prefer fourth type of making valence electrons present in the valence band to be available in the conduction band. That fourth type is which one? It's a doping concept. Okay, we will not provide any temperature to make the valence electrons to move towards conduction band. We will go for doping a pure semiconductor or an intrinsic semiconductor. That process we will use for the semiconductor devices. Fine. So now I'll move to what are semiconductors and certain semiconductor physics. Okay. Now what are the semiconductors? These are the materials which are having 4 valence electron in its outermost orbit or outermost shell. So 4 valence electrons, why that is very important? It's very simple. For a chemical bond to happen, in the outermost orbit, it can have either a 0 valence electron or 8 valence electron for perfect chemical bonding. Okay, but what happens here? 4 valence electron, if they are in the outermost orbit, then 4 is a midway between 0 and 8, right? As a part of which these 4 electrons are very loosely bonded with the atom. So this will make the very small amount of energy is enough for us to make those 4 electrons to be available for the electric conductivity to happen. Okay. So now best examples for the material having 4 valence electron in its outermost orbit are silicon and germanium. You people may even ask, like, why can't we consider a carbon for the semiconductor material? Carbon, even though they have 4 valence electron in its outermost orbit, what happens, energy band gap of the carbon is very high, which is more than 5 electron volt. So as a part of which we people are not considering carbon for the as a semiconductor material. So silicon and germanium are the best examples. We people usually prefer for the semiconductor material or semiconductor device construction. Okay. Now we will see what is the physics behind silicon and germanium. Okay. Physics implies what is the atomic behavior of the silicon and germanium. We can see here there are 14 electrons present with respect to silicon. 14 is a atomic number of silicon, right, which gives us 4 valence electron in its outermost orbit. Why? It is very simple. 2s2, we may be having 2s2 to 2p6 like that, right? So as a part of which in the outermost orbit we will have a 4 valence electron. When we come to the germanium, its atomic number is 32. Here also in the outermost orbit we have a 4 valence electron. If we would like to see actual atomic structure for both silicon and germanium, we can easily find there are 4 valence electrons revolving around the outermost orbit. See, first, second, third and fourth. Okay, so these are the 4 valence electrons present in the outermost orbit for the silicon. So they were very loosely bonded in the atomic structure. Coming to the germanium, we can find here for germanium also there are 4 outermost orbit electrons, 1, 2, 3 and 4. Okay, so as a part of which they will be used as a very good semiconductor material, because its energy band gap is also lying between 1 electron volt to 3 electron volts. So that is the major reason why we people are using silicon and germanium as a semiconductor material. Now we will move on to next concept. What are the different types of semiconductor? So coming to the semiconductor types, initially we will have intrinsic and extrinsic semiconductor. Intrinsic semiconductor is a pure form of semiconductor. It implies pure silicon and germanium slabs. Intrinsic semiconductors are the pure form of semiconductor which implies silicon and germanium pure slabs. Okay, slab means it's a structure, fine. Slab means a solid structure, rectangular solid structure, fine. So coming to extrinsic semiconductor, it is an impure form of semiconductor. Impure means here to the intrinsic semiconductor, we people are adding certain impurities to come up with extrinsic semiconductor. As a part of impurity, we come across two different types of extrinsic semiconductor. Example, P type of extrinsic semiconductor and N type of extrinsic semiconductor. Okay. Now what is doping? Doping is a process of adding an impurity to an intrinsic semiconductor to make it as an extrinsic semiconductor. You can see in the last diagram it is shown. Intrinsic semiconductor to which we people are undergoing through doping process to come up with extrinsic semiconductor. Okay. What is doping? It is a process of adding an impurity to an intrinsic semiconductor. Fine. Now, how do we add the impurities to the intrinsic semiconductor? We will observe. See, this is a P type of semiconductor we would like to construct. For that, to the intrinsic semiconductor, we people are adding trivalent impurity to come up with P type of semiconductor. Okay. Trivalent impurity implies what? Trivalent impurity implies what? It is very simple. Trivalent impurity means in the outermost orbit we will be having 3 valence electrons, correct? In the outermost orbit we will be having 3 valence electron. Fine. So what are the elements in the periodic table which have 3 valence electron in its outermost orbit? Yes, can anyone think on it? Okay, don't worry. So we will have it. Okay. On doping intrinsic semiconductor with a trivalent impurity, we will be able to get a P type of semiconductor. Right? So these are all the different trivalent impurity: boron, aluminium, gallium and indium. Okay. In the periodic table, all these will have 3 valence electron in its outermost orbit. So now silicon and germanium, we people use silicon and germanium which are pure semiconductor, and we dope them with a trivalent impurity to get a P type of material like this. Okay. You people may even observe that in the P type of material we are having large number of holes like this. Okay. Large number of holes and very less number of electrons. Usually these electrons are due to temperature. Okay. They are of very less, because in the P type of semiconductor we are able to get a we are able to generate, or you can say like P type holes are being generated. What is hole? Hole is a vacant place of an electron. Hole is a vacant place of an electron. In the P type of material we could be able to generate those holes, and the majority carriers in the P type of semiconductors are holes. Let us observe how we people are getting a hole for each trivalent impurity. Let us observe this diagram. So you can observe here, silicon is a 4 valence electron atom. So we are using 4 different silicons which are being done a covalent bonding with boron. So boron is having 3 valence electron. So you see, I will take a cross for the silicon electron. See, I am taking a cross for the silicon electron. Okay, there are 4 silicon electron, right? See, there are 4 silicon electrons which are covalently bonded with boron electrons. See, boron electrons are, I am taking a square, okay, so that it will be easy for you to understand it. So boron electrons are 3, right? So 3 boron electron. But why 3? Because boron is having 3 valence electron in its outermost orbit. When you see, for the perfect chemical bonding to happen, there should be 8 electron in its outermost orbit, as a part of which this hole is created extra. So that is how each element or each atom of trivalent impurity will lead to one hole. Okay. If you take a 1 mm square of P type of material, you could be able to get around lakh together electrons, which are sufficient enough for us to take part in the electric conductivity. Fine. So now you can see here, trivalent impurities are also called as acceptor impurities, because hole is a vacant place where we can accept electrons, right? So what are the materials we use to construct the p-type of semiconductor? Boron, gallium, indium, right? Baggy. You can remember what are the materials used for the p-type of material semiconductor construction means baggy. You can remember. You can see here what is baggy: boron, aluminium, gallium, and indium. Right? Boron, aluminium, gallium, and indium. So these are the trivalent impurities we use to construct the p-type of semiconductor. Fine. I hope you understood p-type of semiconductor. Now we will move on to n-type of semiconductor. So n-type of semiconductor, how do we construct? It is very simple. To the intrinsic semiconductor, I will dope by using pentavalent element to come up with n-type of semiconductor. Okay. So on doping a intrinsic semiconductors with pentavalent element, I could be able to get a n-type of semiconductor. Fine. So what are the pentavalent elements? Phosphorus, arsenic, antimony, and bismuth. Phosphorus, arsenic, antimony, and bismuth, these are the pentavalent element. Okay. These impurities we will add to the silicon and germanium to come up with a p-type of material. In p-type of material, you can observe that electrons are the majority carriers. Why? It's very simple. Pentavalent element will lead one free electrons free. Will lead one free electron free, and the holes are very less, and these holes are coming from the temperature effect. Okay, these holes are coming from the room temperature effect, and the electrons are generated by the pentavalent element. So as a part of which, in case of a n-type of semiconductor, majority carriers are electrons and minority carriers are holes. Fine. Now we will see how each pentavalent element is leading to one extra electron. Okay, let us observe this. Yes, fine. You can observe here. So there are 4 silicon atoms. First silicon atom, second silicon atom, third silicon atom, and fourth silicon atom. These 4 silicon atoms are covalently bonded with antimony. So you can observe here, first silicon atom electron, second silicon electron, third silicon electron, and fourth silicon electron. Now how many electrons are associated with antimony? See, first electron associated with antimony, second electron associated with antimony, now third electron associated with antimony, and fourth electron associated with antimony. Currently, how many valence electrons are present in the antimony? There are 5. You can observe squared base electrons are of 4, means one extra electron is pending with the antimony, and that will be available as a free electron for the electric conductivity in the semiconductors. You simply think one antimony atom is leading to generation of one extra electron, but if you take a 1 mm square or 2 mm square or 10 mm square this slab of n-type of material, at that time you could be able to get a lag together free electrons which are enough for us to drive the current electric current in the semiconductor material. Fine. I hope you understood what are n-type of semiconductor, how to construct them. Now we feel what are the materials used for the pentavalent n-type of semiconductor. They are called as pentavalent elements or the impurity. They are even called as donor impurity. What is the major reason for the donor impurity is to be said? It's very simple. Electrons are donated by the antimony. That's what the reason is, donor impurity. Fine. Now, how do we remember them? How do we remember the donor impurity? It's very simple. You can see like PAB, PAAB. Okay, here it is, sequence is something different, but you can observe from this diagram, you can easily observe that you can easily remember n-type of materials, impurity materials, right? N-type of impurities or pentavalent impurity or the donor impurities are PAB. PAB means phosphorus, arsenic, antimony, and bismuth. Okay, so I feel you understood the concept of n-type of semiconductor. Now comparison between n-type N-type and P-type of a semiconductor. It's very simple. N-type semiconductor will lead to extra electron. Okay, will lead to the generation of extra electron. P-type of semiconductor, it lead to the generation of a extra hole. Fine. Next, what are the materials used for the what are the impurity used for the N-type of semiconductor? They are called as donor impurities. What are the examples for those donor impurities? They are PAAB, phosphorus, arsenic, antimony and bismuth, right? So PAB are the materials used for the N-type of semiconductor construction, right? So this B goes to bismuth, keep that in mind. Coming to P-type of material, what are the material used for the P-type of semiconductor construction? They are called as acceptor impurities. Okay, what are the examples of acceptor impurities? Boron, aluminium, indium, gallium, correct? Aluminium, boron, aluminium, indium, gallium, or gallium indium you can say, which is ending with then they are all coming under, usually they are coming under acceptor impurities, right? So this is three different comparison. One is generation of extra electron here and generation of one extra hole here. The impurities used for the P-type of material is acceptor impurity. Impurities used for the N-type of material is donor impurity. What are the examples of donor impurities? These are all the examples of donor impurity. What are the examples of acceptor impurities? These are the examples of acceptor impurities. Then what is the majority carriers in N-type of material? Electrons are the majority carriers in N-type of material. What are the minority carriers in N-type of material? Holes are the minority carriers in N-type of material. Now coming to what are the majority carriers in P-type of material? Majority carriers in P-type of material are holes, and minority carriers in P-type of material are electrons. Fine. So these are very simple comparison between N-type and P-type of material. Thank you, dear friends. I hope you understood the concept of what is semiconductor, what are the types of semiconductor, and what are the comparison between N-type and P-type of a semiconductor. Thank you for your patient listening. We will see with a new concept in new upcoming video. Thank you.